the tissues, and then capillary exchange. So we're going to leave, mostly leave the arterioles and venules and go actually into the capillary beds. So the ones we're focusing on are capillaries that are going to be the more common one, the continuous ones, and talk about the pathways that things leave and enter and the forces that are driving those. So in order to do that, we want to regulate perfusion because we don't have enough blood in our body to perfuse all tissues all the time. So that's what we're going to start with. Once I've kind of recapped where we've been, we're actually caught up, which is really good. I had anticipated being a little behind, so I gave 2 full lectures to hemostasis, but we're caught up. So I'd like to make sure that this part is pretty solid before we go on into perfusion and then into blood. So blood is actually on the syllabus today, and we will probably start that, and we'll start those lecture questions I assigned for today, but we may not get very far into them, but don't panic because we'll have time. But there is a real conceptual shift today between regulating how blood is flowing and how it exits the heart, and then really just looking at what is being delivered and how it's being delivered and how does blood carry those things. So I'm going to start with a figure I made. It's actually in one of our, going into one of our PowerPoint slides. So I'm going to share that screen with you if all works well. Okay, so nothing on here is new. It's all, let me make this a little bit bigger so we're not being distracted by all the other stuff I have on my desktop. We have been focusing, other than the anatomy, we've been focusing almost entirely on this idea of cardiac output, because even when we were looking at how the heart contracted, what regulated its contraction, the whole point of contracting the heart is to get the blood out of it and send half of it to the lungs and half of it out into the systemic circulation. So as I have been drumming, the book and most of the focus of this is, of course, on the systemic circuit. But remember, all of the things we're saying are also true for the pulmonary circuit. So that half of the blood that's exiting the heart is actually going to the lungs. We will come later to the lungs, and when we do the respiratory system, look at how everything's kind of a little backwards there. Remember, veins are arteries, arteries are veins. We're going to be picking up oxygen and releasing CO2 instead of the other way around. That we're going to all do in the respiratory system. So hang on to that because we're going to revisit all this stuff. And one of the reasons I want to make sure it's solid is really it touches on most of the semester, where, again, when we talk about some of the other organ systems, we're going to be focusing on, well, what does the sympathetic and parasympathetic do? How does it change blood flow? And what are the consequences of that in some of the other body systems, like the kidney, digestive system, respiratory system? So this stuff needs to be pretty solid in your understanding because we can't leave it behind. It's going to follow you through the whole semester. So central here I put is cardiac output, and on the left side over here is what we started with, looking at the pump. And we had a simple formula where we took stroke volume and multiplied it by heart rate. So you can see that heart rate is directly influenced by the sympathetic nervous system, and it will generally increase the heart rate. while at rest, your parasympathetic is putting a little bit of a damper, a suppression on heart rate, because you need cardiac output to match what the body's demands are. So when you are delivering, if you're Amazon, you're delivering packages, you're going to try and deliver it at the rate it is being asked for. Maybe Amazon's not a good example. Maybe it's more like supplying a factory with the parts that they need to build whatever they're building. You don't want a big backlog and extra going there. You want it to be matching the use by that particular factory. So the same idea here, tissue at rest needs a lower cardiac output than tissue once it is becoming metabolically active. And that typically, those increases are stimulated through the sympathetic nervous system. So the emergency exercise, even embarrassment, embarrassment is probably a preparation to doing something like emergency, or excitement is a preparation to doing more physical activity where cardiac output needs to go up. So central here we have the sympathetic nervous system, and remember that is, let's give it a different color, like go back to black. That's central because I'm putting it here because it's the faster way of getting a change in cardiac output. It's neural. You have axons that are growing out to the heart and dumping norepinephrine, epinephrine directly on autorhythmic fibers of the SA node, say, to cause the heart rate to go up. It's also sending fibers to the contractile, and those are going to act to increase the blood pressure, right? Because they're going to contract harder. Contractility is going to go up. In addition, sympathetic is going to also talk to the vessels. So over here on this side are the pipes, the vessels. So the book uses this expression, total peripheral resistance. So that is how much resistance to flow through all of the vessels of your body, sort of on an average. So I'm going to stop there for a second because we talked about this formula, but we didn't really put it up here on the board. One of your groups talked about all the factors that can contribute to resistance. And the main factor here, the primary factor, maybe I'll make that one red again, is going to be diameter. Oops, sorry, go away.
I'm sorry.
Go away, Siri. Yeah, I'm glad you're apologizing, but I want you to go away. Siri. Hey, Siri. Go away.
Okay.
Sorry. Can't control my Siri. So the diameter is the primary way in which you can regulate total peripheral resistance. So one of the things that seems contradictory, if you step back and look at it, is that if I am trying to increase cardiac output, then on this side, what I do with my sympathetic is I increase resistance. If I increase this, it's in the denominator. It ought to decrease cardiac output, right? So in order to actually make cardiac output go up using this side's formula, that means I have to make an even bigger change in the pressure gradient. So I know this is math really early in the morning, which may not be fun, but does that make sense? If there's a question, I'm going to put chat up there too. So if you feel more comfortable asking it in chat, then ask the question in chat. So this seems sort of contradictory that in order to get greater cardiac output, our sympathetic is increasing the resistance by causing vasoconstriction. I'm going to give you a minute. You can put anything you want in chat. Make sure you understand this so far. And if not, maybe you can just give me a thumbs up and I'll look at everybody's picture over here onto the side. I'm not seeing any thumbs up. So either you, oh, I got a thumbs up. Thank you, Augustine. So if there is a question, if this is something that's not making sense, you've got to ask it. So we can get this down. Okay, we got another thumbs up. If you don't know where the thumbs up are, you go into reactions, and that will give you the little menu for the thumbs up. Okay, so someone asked, could I repeat the last statement, which seems contradictory? Okay, so remember, if we just ignore what's off to the left here at the moment, if we want to increase cardiac output, the sympathetic causes a greater increase in resistance of these vessels. It makes this number in the denominator bigger. Now, the way it does that is it causes vasoconstriction, and especially if you kick in the angiotensin II, you're going to get lots and lots of vasoconstriction. The pipes are going to get smaller in diameter. It's going to get harder for blood to flow. Less will flow in that laminar flow way where it's going fast through the middle, and more is going to be rubbing the outside, having greater resistance to flow. So the only way that that's going to result in there being an increase in cardiac output using this formula is if you can more substantially increase this pressure gradient. So delta P, that's a delta up here, the difference in pressure is the pressure gradient. So what I mean by that is if you're at an artery over here and you're going into an arterial, and we're going to look at it again in a second. Remember that graph that showed mean arterial pressure as it drops? You know, this might be at 90 systolic, and this one, it drops. Remember, due to resistance, it's dropping, might be at 70. So that is a gradient, 90 to 70. That's what we're looking at for delta P. The source of delta P, of the higher pressure to cause that gradient, is of course the contraction of the heart. It's what's happening over here on the pump side of it. So the pump is the only way you can make delta P get bigger. Are we okay with that? Any questions? Again, I'm going to give you a second to put something into. You can do it privately, you can do it publicly, whatever you would like to do. Okay, so I'm not seeing anything, so I'm going to assume that makes sense, even if it's just mathematically. If I increase this, say, by doubling it, I have to more than double this in order to make that go up. Well, how does that happen? That happens because of the Frank-Starling law and preload. Because what are we doing when we increase this total peripheral resistance? When we do this, this is in order to increase venous return, which leads to an increase in end diastolic volume, which leads to an increase in preload. So remember this law. This law is saying preload is the strongest factor in determining cardiac output. So by increasing preload, by making those sarcomeres closer to their optimal length, you get a much stronger contraction, stroke volume goes way up, and that makes your delta P go way up, because delta P is that bolus of blood that is being ejected out under pressure. Am I losing anyone? Any other questions? I'm going to stop again here.
You said that by making the sarcomeres closer to optimal length, stroke volume goes way up. And then what was the second bit of what you said? So
since stroke volume is that bolus of blood, the amount of blood being forced into the pipes, and it's being forced in by a stronger contraction, that makes this number right here, if you increase stroke volume and preload, that has the strongest influence on the delta P and makes that go up. And that's what you need to have happen if you're going to use an increase in resistance. If the denominator goes up, you got to make the numerator go up even further. And the way you do that is return more blood, make end diastolic volume go up, increase your preload. Since preload is the major factor in determining stroke volume and in determining cardiac output, that is making the heart work harder, getting more of a pressure behind the blood and increasing delta P enough to increase cardiac output. There are a lot of variables here, so please ask if there's one of them you're not getting. Okay, so I don't see anything in chat, and nobody's speaking up. So if you play with this, you think about it as a whole system rather than just what's happening in the heart, what's happening in the vessels. This is putting it together. How what's happening in the vessels influence end diastolic volume, therefore influences cardiac output and influences delta P, because it makes the heart contract harder, which makes a greater pressure. So I'm saying it hopefully in enough different ways that you can grasp onto this idea. So I threw angiotensin 2 in there because, of course, angiotensin 2 even more substantially, these guys, sympathetic and angiotensin 2, really cause vasoconstriction, and therefore they cooperate together to do that. If you're using your sympathetic, your local tissue signals might be able to override that vasoconstriction, and we are going to talk today about who are those local signals that could override this. Once you have both of these present, typically those local signals cannot override it. You've got two things saying vasoconstrict, and angiotensin 2 is a stronger stimulus to do that than just sympathetic alone. Now, what I didn't put on here, which we discussed last time, is the effect of angiotensin 2 on blood volume. But if you affect blood volume, of course, you're affecting end diastolic volume, you're affecting preload, and you're affecting strength of contraction and therefore stroke volume. All right. I'll wait a second before we go any further. Okay. Are we all right then? So the reason I stuck this into the PowerPoint is because I wanted to re-show you the next slide. This slide is, let me get the essays, is the one referred to in the first sentence of essay 4. And it asks you to literally describe, using numbers, no key values, describe how delta P, and where is delta P on here? Well, it is the difference between the mean arterial pressure at one point, like say it's typically 93 when you're using 120 over 80 for systolic and diastolic. And as it goes down this slope, if I pick some other point, this arterial here, maybe it's at 60. Delta P is 93 minus 60. It's the difference between the pressure closer to the heart and the pressure at one point in an artery and pressure at another point in an artery. And that's what's pushing the blood through the vessels. So in lab today, you're going to be dealing with these. We've already defined them. We talked about them earlier last time, but you're going to be dealing with actually doing some calculations. And I mentioned last time there were two formulas. Either one works just as well, and we could even in lab demonstrate that. You can stick, 80 and 40 in here, and you'll get 93. And if you stick 80 and 120 in here, you'll get 93. You could prove that to yourself. So both formulas work, whichever one you want to use. So the other thing we're going to be doing very shortly is looking at what the mean arterial pressure is when you get to the capillary itself. So I said you need to know this number. Let me see if I can wake this up again. 41515 and write on it. So as it enters the capillary, let's go back to black. So it's going to be at 35 right here. This is going to be, the number we're going to be using on average is about 35 millimeters of mercury. So why it dropped that had to do with all the resistance factors, the diameter changing, the length getting longer, because there are many more branches as you go down here. So this is what essay 4 in the beginning asked you to talk about. Now viscosity shouldn't be changing, so that would be an abnormal situation, but all the others could be changing. By the time it leaves the capillary on this side, we're going to know this number is 17 millimeters of mercury. So what's pushing the blood through the capillary bed is a delta P, a mean arterial pressure difference of 35 to 17. So if I remember, it's the last group F that's going to use these numbers, but these are mean arterial pressures. So they're going to use a different term. I almost wish they didn't have a different term, but it's exactly the same thing as what we're going to be talking about as hydrostatic pressure. So just to orient you to that for when we get there. Now, before we go there, on the last question from last time in group F, we have group E, and group E is going to determine whether blood even goes through this capillary bed. And the way it would avoid that capillary bed, I'm reminding you, hopefully, is that there are these things that are called meta-arterials. So not every capillary bed uses a meta-arterial, but every organ has these meta-arterials so that you can divert blood from the capillary bed here directly to the vein in order to increase venous return more rapidly. Or you might be doing it because these local conditions say, I'm not doing anything with that tissue right now. Its metabolic rate is low. It doesn't need oxygen. It's got plenty of oxygen and glucose, and it hasn't generated many waste products. And so the local conditions here are going to tell these sphincter muscles to close because we don't need much oxygen. So once again, we're going to be discussing intrinsic factors like the local condition factors and extrinsic factors like sympathetic norepinephrine, epinephrine, or angiotensin II on these sphincter muscles. So with that little bit of anatomy, the first group E, and hopefully you remember who your spokesperson is, can you address what are the extrinsic factors? So we're on lecture question 15 in the vessel set of lecture questions. Can somebody go through some of the extrinsic factors? Do you have a spokesperson for Group E from last time?
I can go ahead and do that.
Okay, thank you. It's Alexis, right?
Senna.
Oh, Senna. Okay, yeah, please go ahead.
So in terms of extrinsic factors, in the short term, we have the norepinephrine, which would vasoconstrict. In the long term, we'd have the angiotensin II, which leads to aldosterone and ADH, which increase water reabsorption. That's for extrinsic.
And there's one that can lead to dilation of the arterioles that we went over last time. Sorry.
Is it ANP?
Yes, exactly. Now, ANP, angiotensin II, are not just acting on these sphincters. Of course, like Sana brought up, they're acting on the smooth muscle of the artery and arterioles. But in addition, they're acting on these sphincters in the meta-arterioles so that they'll close down and blood will flow more rapidly. So extrinsic in general are going to, maybe there's not much room to write on this, but if it's an extrinsic factor that's doing this, oops, why is it not drawing? There we go. It's extrinsic. It's usually doing it in order to increase venous return. So the goal for the extrinsic is going to typically be to increase venous return and end diastolic volume, and therefore increase mean arterial pressure. Are we okay? This is going to be to help your whole body. So it might be, if it's extrinsic, it might be doing this because you have low blood volume and you need to send blood away from this organ in order to have enough pressure to distribute blood to any particular organ. So maybe you'll be sending it away from your skin so that you can send it to your brain because you want to make sure your brain is getting enough oxygen. If you're exercising, you might be sending it away from your digestive tract here so that you can send more blood to your skeletal muscles. Are we okay with the idea of extrinsic factors? Okay. All right. How about someone else, or it can be Sana, whoever can remember and step up and talk about the intrinsic factors that are also going to play here, have a role here.
I can go ahead and try to do it.
All right. It's big, I know.
So for intrinsic factors, you have, they will typically override the extrinsic factors in the organs that need the blood more critically. So you have two classes, either vasodilators or vasoconstrictors. So for vasodilators, you'll have increase in hydrogen ions, potassium ions, as well as CO2. Those are the metabolic factors that get released. And then other factors that are released are the prostacyclin, which would inhibit the platelet activation, as well as paracrine signals that are released from the endothelia, which would be the prostaglandins, adenosine, and nitric oxide. So these are all vasodilators. And then for vasoconstrictors, we have the endothelins, which is a metabolic factor that gets released when oxygen is high. And I think that's what I have for vasoconstriction. Other than that, the myogenic factors, which are meant to protect the walls of the vessels from bursting.
All right, that's brilliantly done. And there is a summary slide of this, which is another reason I showed this. But note that the goal here is for this tissue to say, hey, I need oxygen or I don't need oxygen and nutrients delivered. I've got a lot of waste products or I don't have a lot of waste products. So they have dilators and constrictors, and those are acting to make the delivery and the removal of nutrients and the removal of waste in balance with what this particular tissue needs. Is that saw sound interfering with you guys hearing?
It's not too bad, at least for me.
Okay, all right. Let me know if it does, because otherwise I'm getting up and down to let the dog out. The door is open since the air is good today. All right, let's take a look at the slide. I'm going to zoom over to that slide whoops, except it doesn't want me to do it there. It wants me to do it over here. That's showing these factors. So this is your summary of your extrinsic and intrinsic. So over here is the extrinsic. Let me point with the pointer. And you can see there's neural and there's hormonal. And these over here are the constrictors that we've talked so much about. Angiotensin 2, antidiuretic hormone is a vasoconstrictor. Remember, sometimes it's called vasopressin. And of course, epinephrine and norepinephrine. So what do we have on the dilator side? Well, we can just decrease the amount of sympathetic. There's no parasympathetic innervation, so we could just decrease that. Or in cases when blood pressure is very, very high, you might be releasing ANP, and that will cause dilation. So extrinsic is where we've been mostly talking about it, but here are these local signals that might be able to override a sympathetic tone here. It's typically can't override angiotensin 2 plus the sympathetic tone, and certainly not if you had ADH angiotensin 2 and increased sympathetic. Those sorts of situations would be like when you have really low blood volume, then many of your local organs are going to be vasoconstricting despite needing the blood being needed in that area, and these metabolic factors that are local saying dilate this. So they've broken this up into two types of controls. One is metabolic and one is myogenic. Now, the next group, there is going to be a discussion about this myogenic, which we'll come back to, although Sana did a nice job of saying, really, its job is to protect the walls of the capillaries and of the small arterioles by not letting a huge surge of blood enter the delicate capillaries. Remember, capillaries are only simple squamous endothelia. There's not much structure to them. They're pretty delicate. So let's spend most of our time up here dealing with these metabolic, and we'll talk about the endothelians as well. I added to their list prostacycline, and we're going to talk about that in a little bit. And these prostaglandins and adenosine and nitric oxide, we're going to lump these guys together, and then we're going to lump these guys together. So if I can maybe I'll try and make this bigger by going to the slideshow. Make it a bit bigger here. So what I just said is we're going to lump these guys together. And why we're going to lump those guys together is, if you look, these are the sorts of things that have to do with metabolism. If the cells of the body that are outside this arterial and are being served by its capillary bed, if they're going through high metabolism, you're exercising, then you're going to be increasing the release of CO2. The oxygen level in that tissue is going to be decreasing. You're going to be making acidic waste products. And therefore, now I've got the bird chirping too, so let me close the door for a moment. So H plus is going to go up and pH is going to drop. Just because they're releasing metabolic waste, maybe it's a muscle and it's lactic acid into the interstitial fluids, and it's really the endothelia, the lining of these arterioles, that are detecting these things. So now, why potassium would be high? This would be especially true in a muscle where you're going to have a lot of action potentials and therefore a lot of repolarization phases on those action potentials where potassium is exiting. So you might not always have a lot of potassium if there's not a lot of action potentials in that particular tissue. But something like muscle tissue or nervous tissue, you would definitely see a rise in potassium. So let me see if that group of metabolic waste products makes sense. Does everybody feel okay about that? Is there a question? Think about any questions you might have. Okay, so what about these others? Prostaglandins, adenosine, and nitric oxide, these are released locally, and many of them are released by the endothelia. Now, why they know to release them is because of these conditions. So in a way, this causes, maybe because I shouldn't be pointing at just the prostacyclin, but this causes the release of those things by the endothelia. And it's really those things that are causing the vasodilation. So the conditions trigger the release of things like nitric oxide and prostacyclin to allow for there to be vasodilation. Adenosine may be being released as almost like a neurotransmitter, and it would be inhibitory. And if you go back and look in the neurotransmitters we studied, ATP is one of them. So it turns out adenosine can also act sort of like a neurotransmitter. Nitric oxide was one of the gaseous neurotransmitters on our neurotransmitter list. Now I want to just spend a second talking about prostaglandins, because this is a large group of molecules. Oops, I'm sorry, things are moving on this. And it's often going to be used kind of indiscriminately. There are many, many types of prostaglandins. So it's not that every prostaglandin is a vasodilator. There are specific examples. And one of those is prostacyclin. So over here, I did put down that prostacyclin is a kinosanoid. Now we talked about those way at the beginning of 103A. You've probably totally forgotten about them, but embedded in the lipid bilayer of all membranes, all plasma membranes, are free fatty acids. And when you damage or, even slightly damage the plasma membrane, these fatty acids are escaped from the lipid bilayer, and they act as local vasodilators. We're going to really see this in the immune system when we talk about the process of inflammation, which causes vasodilation. So hold on to that thought, because we're going to come back to it. One of the reasons I picked out prostacyclin, and this is just, I don't test you on this because it goes beyond the scope of the class, but certain anti-inflammatory drugs which fall under this class, NSAIDs, these would be things like ibuprofen, if you've taken that, or Aleve, not Tylenol. That's an analgesic, so lowers pain response. These things lower inflammation. Well, inflammation is local vasodilation. So if you've twisted your ankle, then there's a lot of vasodilation going on in your ankle. You don't like that. So you end up taking something like ibuprofen or Aleve or something like that, nalproxone. Those drugs act to inhibit prostacyclin, and therefore, even though the damaged tissue is releasing these things, its effects are being at least partially blocked by blocking this prostacyclin. So the book does mention prostacyclin. Now, there are other echinocanoids which fall into the class of prostaglandins that are released for other reasons. And we will be coming back to them, but most often the book will just keep calling them a prostaglandin. So realize there are many types of these things. So know this list. Understand who is a vasodilator. There are vasoconstrictors, and I believe Sana also mentioned the endothelians, which is a nice name because, of course, it tells you who released it, the endothelia, just like these guys. And this would be released when local conditions are saying, I don't need to have blood supply here. So what would trigger this guy to be released would be things like high oxygen. Sorry, it's kind of a fat pen here. Low CO2 levels, low H plus or higher pH, and low potassium. Those conditions are saying this tissue doesn't need more oxygen delivered and doesn't need more waste products removed. So it would cause the endothelians to be released, and that would lead to local vasoconstriction, closing of those sphincters, and the tissue perfusion would go down. There is something else we're going to run into when we do blood clotting shortly, and you can add to this list because we're going to talk about it shortly, thromboxanes, which is quite a mouthful. Now, these guys are vasoconstrictors, and they also will be involved in preventing platelets from starting a blood clot. So many of these molecules have multiple reasons to be released. And once again, these are released by the endothelia. So I mentioned quite a while ago that these endothelia are very busy little cells, and they're constantly monitoring their environment around that tissue. If they're in those small arterioles, and they're the sphincter muscles of the meta-arteriole, and if the conditions are well oxygenated, then they're going to be releasing these vasoconstrictors. And if they are poorly oxygenated and lots of waste products around, then they're going to be releasing these vasodilators. Okay, so this is just to remind you, we're in essay 5 now, talking about autoregulation. That means what are the local controls that the tissue is using in order to regulate blood flow to that tissue. Okay, so let's go to the last group, F, and hopefully we have a spokesperson for F. Is there somebody out there that's a spokesperson?
Yeah, that would be me.
And me is?
Noah.
Noah. Okay, Noah. All right. I guess you get elected a lot to be the spokesperson. So can you talk about the myogenic reflex?
So the myogenic response or effect is like a protection method that capillaries and arterioles will utilize to prevent bursting because of like the extreme pressure from the bigger arteries. So basically, whenever the smooth muscle will experience increased pressure, there's going to be stretch that comes along with that. So to counteract that, the vessel will then vasoconstrict. But on contrast, it can, if there's like less pressure, there's less stretch, so it's going to vasodilate.
And what part of the vessel what tissue is doing this?
Do you mean like the sphincter or?
Yeah, and what is it made out of? What kind of tissue subtype?
Smooth muscle?
Clearly muscle, but it's smooth muscle. But what kind of smooth muscle?
I don't have that in my notes. Multi-unit?
Jasmine.
Oh, I think I heard something. Did you say it?
Is it multi-unit?
It is multi-unit. And so that, let me see if I exit this. And I forget how to do that now. Here we go. We can discard that. If we go back in these notes, I think it's in this one. Maybe not. Maybe it's in the other one, heart. You go to your slides somewhere. I have the smooth muscles compared. I thought, maybe it's in the, no, I thought it was in the vessel one. Should have found this before. Let me find our vessel one. Probably that's up here. I probably just went by it too fast. Remember, I made those big concept maps comparing the types of, I'm not finding it. I want to find it. Let me try once again. I don't think it would be. Maybe it's not in the cardiac output, I'm sure. Could it be in the heart? Maybe I didn't pass over the right set of slides here. So not seeing.
Are you looking for the slides of two subtypes of smooth muscle?
I am, that concept map that I made. Let's leave that since I'm obviously struggling to find it. And
I found that it's in the lecture for the first midterm.
Yeah, and I think when I copied it on my lecture slides to the iPad, I think I didn't transfer the one that had that embedded in it. So that's why I don't have it here. So let's just go to the other program here and just use another note. So we had two types of smooth muscle, and I'm not going to go through all of this, but please look up that. And one of them is called multi-unit. And the other one is called single unit, or sometimes called visceral, which is telling you where you find them. We're going to deal with both of these subtypes this semester. So again, make sure you go back and review this stuff. We won't see single unit for a while, but because it's mostly when we get to the digestive system, and yeah, it's probably, and that's pretty much it. I mean, there is some in the reproductive system too, but it lines hollow organs. The multi-unit, the vast majority of the multi-unit line blood vessels. So most of it found in blood vessels. And particularly the tunica media. This is not writing, media. And one of the key differences between these two is their response to stretch. So when you stretch multi-unit, you don't need any neural input or anything. Stretch leads to constriction. It activates there's a sliding filament theory. There are no sarcomeres, and I don't understand how this works. I'm not sure if anyone does, but when you physically move the actin and myosin further apart from each other on the thin and the thick filaments, they do have thin and thick filaments, they just don't have sarcomeres. They're arranged in that net-like thing, if you remember from 103A. But when they get moved, there is just a mechanical reaction to that. Doesn't require an action potential, doesn't require any neural input. It will cause them to constrict. So it's almost like there is a set point. I'm going to put it in parentheses. There's a set point length to this type of smooth muscle. And just like Noah mentioned, if it's normally the thin and the thick are at some sort of relationship to each other and you stretch them, they're going to bounce back to that relationship that they had before. If they're forced by there being less blood pressure to being shorter than they like, they're going to dilate and try and get back to their set point length, as it were, a relationship between the thin and the thick filaments. The opposite occurs in single unit muscle. And you'll be glad for that with your digestive tract, because if it constricted when you stretched it, well, the way you could stretch it is eating something. You don't want that to happen. You want it to accept more food. Well, assuming you don't want to lose weight, you want to accept more food. So this relaxes when it's stretched. And again, I don't know the actual mechanism, but it does not require any kind of action potential, any neural input. It's just an automatic way in which these respond to the stretch of the length of the particular smooth muscle fiber. Okay, so the other feature I think you should, let me use a different color maybe, focus in on is this one. In order to contract, to actually be stimulated to contract, you require a norepinephrine, epinephrine, norepinephrine, epinephrine, angio-2, ADH. It requires an extrinsic signal to contract. And later we'll come back here. This doesn't. This has a pacemaker. It's got cells that act kind of like the SA node and synchronize everyone. These guys have gap junctions. These have no gap junctions. But they do contract as a sheet. And the way they contract as a sheet is that this acts hormonally. They have their receptors for the signal all over the muscle, all over the sheet of muscle, so that they are all exposed to the signal to contract at the same time. Okay, so in that brief but not spectacular way in which I tried to outline these two differences, let's go back to this multi-unit and the myogenic. The book is going to make it sound like this is a local signal in order to control, that's affected by the local conditions, like, you know, the tissue needs more blood and therefore it has, you know, low oxygen, high CO2, and that's not the case at all. The myogenic response, which is what this leads to, this causes the myogenic, is just regulating or maintaining a certain amount of stretch at a set point level. So when systolic or pressure goes up, like Noah mentioned, and there's suddenly an increase in the systolic pressure, you're trying to use the myogenic to protect the walls of the capillary. So it's not to regulate locally. Its function is to protect capillary wall from a surge in pressure. So even though they stick it in intrinsic, and it is intrinsic because it's a feature of the smooth muscle that's making up that organ, it's not really regulating based on local conditions of metabolism. It's based on local conditions of blood pressure change. So it's in that list, but make sure you understand that difference. Okay, so that brings us to the last question here, which is partly also, maybe I'll just go on to the next page. And I'll just write the numbers. And are you still the spokesperson, Noah, or somebody want to step up and relieve Noah of his chronic duties as spokesperson?
I don't mind answering it if someone wants to take over. It's fine.
Okay. So I'm going to kind of draw the picture as you go that they have in the book. And we're going to make this the arterial side and this the venous side. So tell me about the forces that drive things out by bulk flow.
So there's the hydrostatic pressure, which is basically the mean arterial pressure. And from the arterial to the capillary side, it's going to be 35 mercury, basically. And
that's pushing outward, right?
yes, that's pushing into the venous side, basically.
Yeah.
And to counteract it, there's osmotic pressure, and it's actually 26 coming from the venous side.
And that's pushing
into the arterial.
outward.
Yeah. And then there's like hydrostatic pressure in the interstitial fluid that's pushing into the capillary, but that's 0. And then the osmotic pressure from the interstitial fluid is pulling fluid out of the capillary, which is 1. So net osmotic pressure is going to be 25. So from there, we can calculate the net filtration pressure, which is going to be hydrostatic pressure minus the net osmotic pressure. And it's going to be 10 milligrams mercury. And then that means because it's positive, it's basically going into or outwards of the arterial.
Okay, great. All right. So now let's go over to the venous side on this side and do the same thing.
So the hydrostatic pressure is going to be lesser because the map is lesser because it's more branched and it's just more resistance. So it's going to be 17. And then the net osmotic pressure is just going to stay the same. So we can go ahead and just calculate the net filtration pressure, and it's going to be -8. And that's going to be, because it's negative, it's going into the capillary.
Well, actually, maybe I should do it the other way. Then you'll see it's negative. Okay. So then we're going to put them in the same order here, and we're going to have 17 minus 25, which equals -8. Okay, good.
And there's also the leftover 2. And in your lecture notes, you said that goes to the lymphatic system.
Yeah,
We'll talk about it later.
That after this test, leftover.
But it eventually goes back to the blood.
Yeah. To blood. Okay, great. Perfect. So you do need to know these numbers, although I don't typically worry about these guys. So if you want to just use 25, it's okay. So what is this? Well, first of all, I always make this sort of editorial comment. I think this is brilliant. This is like amazing to me. There's 2 amazing topics we're going to have in my mind. I mean, we've had quite a few already, but I just think this is so brilliant because what you're doing is using the drop in hydrostatic pressure that is occurring, as Noah said, because your capillaries are very small in diameter and highly branched, so they have resistance. And you're using that resistance to drop the hydrostatic pressure so that on the venous side, the waste products can enter into the bloodstream. And how they're drawn in is through an osmotic pressure. Now, we're going to be dealing with that in the very first part of the next set of lecture questions. So we'll see where that osmotic pressure came from in a few minutes, but it has to do with the contents of the plasma of the blood, which is high in proteins. Proteins can't escape the capillary through the capillary's paracellular route, which I think we dealt with when we talked about these capillaries and bulk flow. So they're left behind and they're trying to pull more fluid from the tissue. Now on the arterial end, they're still trying to do that, but the high blood pressure overwhelms that so that the net flow is outward, like he said, of 10 millimeters mercury. That's called the net filtration pressure. So I don't know. I just think it's great. It's brilliant. You know, you just use the fact that this doesn't look like a capillary, it looks like a meta-arterial, but use the fact that you're going to run into resistance, hydrostatic pressure is going to drop, and using that osmotic pressure, you're going to push things, allow things to re-enter the capillary at the venous end. So what can go in on the venous side are going to be waste products, CO2, and what comes out on the other side are going to be things like oxygen, nutrients, you know, and I don't know, maybe you don't think it's as brilliant as I do, but I think it's brilliant. Okay, so any questions on that?
Professor, I have a question.
Sure.
I just wanted to confirm this was part of Essay 5, how it says to quantitatively describe how hydrostatic and osmotic pressure that drive capillary exchange.
It is, yes. It's exactly what Essay 5 is talking about, right in the middle of it. But then it brings up in the last part, what happens if you change mean arterial pressure? So let's take a look at somebody where that happens. Let's say instead of their mean arterial pressure at the hydrostatic end, so let's have this be the arterial, my arterial end here, and instead of that being 35, they have low blood pressure, lower than normal. Maybe they've lost some of their blood volume, but they're not dehydrated, so their osmotic pressure is normal. Their blood is normal as far as its constituents, you just have less. They were bleeding, maybe, okay? So their hydrostatic pressure, let's say instead of 35, let's make it 30. So then their osmotic pressure is the same on the arterial end at 25, and what's going to go out is going to then only be 5 millimeters of mercury net filtration pressure. Are we okay? So what does that mean for the person? Are they able to get as much nutrients out into their cells? Can they service their cells enough to, well, we don't know if it's enough, but are they doing it as much as normal? No, instead of 10 millimeters of mercury pushing things out, you've got only half as much pushing things out. So less of the nutrients that have to move by bulk flow. Now, oxygen can go simple diffusion. Some of it will also go, not much, but some of it will also go through bulk flow. So it might be getting oxygen there, but you're not getting nutrients to those tissues as effectively. Now let's go over to the venous end and see what happens. So you saw 35 drop to about 17. That's about half. We okay with that idea? It goes to about half. So let's drop it again to half because let's say that resistance is about the same and it's going to drop to about half. We'll make it 15. Osmotic pressure is the same. So OP is still 25. And you subtract that, and that means there's an inward flow of plus 10, right? Are we okay? So that's not a plus, I'm sorry. We're not okay, it should be minus 10. It's an inward flow of 10. What's happening to the volume of the interstitial fluid in this person? Increase, decrease. How about in reactions? I think you in reactions. Do I even have reactions on my menu somewhere? If you think it increased, put a thumbs up maybe. Okay, how about what happens to the interstitial fluid and let's say it's decreasing? How many people give me a thumbs up for decreasing? Nobody has any opinion? Be brave. Doesn't matter if you're wrong here. No points associated with this. So 5 came out, 10 goes in. Before we had 10 coming out and, right, here we are, and 8 going in, right? We left 2 behind. Here, down here, we have 5 going out and 10 going in. This is going to lead to a decrease in interstitial fluid out here in the tissue. What's it going to ultimately do for the blood volume, though? It's going to cause the fluid that's interstitial fluid to be pushed back into the venous system and therefore help increase your blood volume at the expense of fewer nutrients to this organ and less fluid out here. That's what happens when you're dehydrated. So one test of someone who's dehydrated, you may know this already, is to pinch their skin. If the skin stays, like a little mound after you've pinched it, that's because there isn't enough fluid in there to kind of to allow it to go back to its original shape. They even look at things like turgor pressure in their eye. So your fluids of your eye get depleted, and this eyeball isn't as hard. That's what turgor pressure is. So someone who is got low blood volume, you're going to try and recover that blood volume from the interstitial fluids, but in doing so, you're depriving those organs of nutrients and of fluid, and that's what dehydration is, causing. Okay. So we're going to return to this after we look at the blood a little bit, and because the last part of it also says, well, what happens if you manipulate the osmotic pressure? But first, let's take a look at what is the source of this osmotic pressure. So we're going to move into the next set of lecture questions. We have about a half an hour. So how about if I set you up, I'm going to stop sharing, and set you up into some breakout rooms. I'm going to make them kind of big because I don't think we're going to have time to go beyond, let's just try to do A and B groups. And then we'll come back and talk about that. Those are all sort of under the heading of the beginning of part of Essay 6. So I'm only going to make 2 rooms and just put half of you in one and half of you in the other room. I don't know why this doesn't happen automatically. Maybe I'll see what happens if I try and make it automatic. Okay. Did that happen? Oh, it did happen. All right. And let's give you, these aren't very difficult questions because they're really answered for you in the slides. So if you got availability of the slides, so I'm going to cut it down to 10 minutes. So we have 20 minutes to talk about those 2. Okay, so are you ready? You're going to be leaving, and pick a spokesperson, please, because we'll try and finish up questions 1 through 5 in the next set of lecture questions. All right, have fun and find your slides.
Hello?
Hello.
Hi, guys.
Hi. Do you know what question she said we were doing?
I was going to ask the same thing.
I think she just meant to answer 1 to 5.
Oh, we're answering 1 to 5?
That's what she said at the end there, right?
Okay.
Wait for.
I didn't pay attention.
2 examples for each. For distributive, the oxygen and nutrients to organ and tissue, and hormones and chemical signals. Regulatory is temperature regulatory, because blood's like a heat reservoir, and the electrolyte balance, and vasoconstriction for volume and pressure. And for protective, I put immunity via white blood cells and blood clotting to prevent excess fluid / red blood cell loss and entry of foreign pathogens. For number 2, the 6 plasma proteins, I put albumin, fibrinogen, and then the 3 globulins, alpha, beta, gamma, and prothrombin. Does everyone agree with that one?
Yeah.
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 Okay, and then just the general functions. Albumin, 60% of plasma proteins, main contributor to osmotic pressure. Alpha and beta globulin do the same thing. They transport proteins that bind to lipids, metal ions, and fat-soluble vitamins. Fibrinogen makes 4% of plasma proteins and is produced by the liver, forms fibrin threads of blood clots. And for prothrombin, I just put it helps with coagulation. And then if someone else wants to do 3, 4, 5.
I can do 3 and 4. So for number 3, it's really small. It's 7.5. Is the U stand for nano or micro?
I think it's micro.
Micro, a micrometer. It has a large surface area compared to volume ratio. So there's more surface area than the regular spherical shapes. And this just increases the amount of oxygen that it can attach to it. It has a biconcave shape, which also increases surface area. And it allows it to be flexible, but also strong because of the spectrum that is in the cytoskeletal network. And this allows it to fold and squeeze through tight spaces. It's anucleated and it lacks organelles. So since it lacks the mitochondria, it doesn't use oxygen because it generates ATP through anaerobic mechanisms. And it makes it efficient for transporting oxygen, but it's short-lived because they only live for like 90 or 120 days. And it has hemoglobin, which takes up 97% of volume. And hemoglobin is a molecule that binds to and transports respiratory gases. Number 4 is, so basically hemoglobin is made up of a heme group and a globin group. Globin has 2 alpha and 2 beta chains, and it's binded to a heme group. And in the center, it has an iron ion in the center. So one hemoglobin can transport 4 oxygen molecules because the iron ions can reversibly combine oxygen. So overall, it can carry like 1 billion oxygen molecules. And it also, the globulin chains can bind and transport carbon dioxide as well. Things that can change the shape of hemoglobin is pH, the number of oxygen bound to it, temperature, and the type of hemoglobin. For example, if it's fetal or versus adults. Yeah. I don't have number 5. I couldn't find that one. And I do have number 6 if, I don't know.
I think we're only supposed to go up to 5.
I have number 5.
I have fetal hemoglobin has a greater affinity for oxygen than adult hemoglobin.
Yep. And the reason it's important is that if that wasn't the case, there'd be no differentiation between the fetal form and the adult form, and obviously fetuses need oxygen too.
I can't hear you.
Oh, sorry. I was just saying that the reason that the fetal form has a greater affinity compared to the adult form is because if it wasn't the case, there would be no differentiation between the fetal form and the adult form, and then the fetal form or the fetus would not obtain an adequate supply of oxygen.
Right. Well, and structurally, the fetal hemoglobin contains 2 alpha and 2 gamma polypeptide chains per globin molecule rather than 2 alpha and 2 beta, as seen in hemoglobin HbA. And then after birth, the liver destroys the fetal erythrocytes carrying the HbF, and the baby's erythrocytes begin producing HbA.
You find that information in the book? I'm sort of curious.
I think so. Yeah. Yeah, that's
Okay.
right.
Do you know what page it is on?
I don't remember what page it was on.
I have an older version of the book, so it probably won't match yours.
Yeah, because I had to Google why, because she didn't really explain it, and it was pretty much what Santa said. Is like they need to have the higher affinity, but it's cool that you found that information. I was sort of curious as to why it happened that way.
Yeah, I was digging for it because I was curious too.
Okay, does anyone want to be spokesperson? I think she's tired of me talking, so.
Yeah, she's probably getting tired of me talking too, so somebody else should step up.
I could do it. If someone could explain number 5, that would be great, because I'm not sure.
Yeah, so number 5, basically, as Dina said, and like histology-wise, they're built different.
Mm-hmm.
She was saying that it has 2 alpha and 2 gammas instead of 2 alpha and 2 betas, as like with adult hemoglobin. As well as for what me and Santa put, fetal hemoglobin needs to be more affinity to oxygen, because if they had the same affinity as their mother, they would pretty much just get the same amount as their mother, but they need a higher requirement for oxygen because
Right,
they're a
it's
fetus.
about transferring the oxygen from the mother to the baby to
Right.
itself.
So the baby's basically stealing the oxygen if you think about it, you know?
Okay,
Right.
I see. Okay, so it has 2 alphas and 2 gamma globulin chains, right?
Mhm.
Instead of the 2 alpha and 2 beta.
Yeah.
And it has a greater affinity because it needs it to be more than the mother's.
Right. Otherwise, the mother would retain all of it, and the baby wouldn't get any.
Yeah.
Think of it like that.
Just think of the little
Okay.
fetus just grabbing the oxygen, you know?
Yeah.
Cool.
Without the affinity, the baby wouldn't get any oxygen.
All right. Cool.
Good job, guys.
I feel
Good
like these
discussion.
have become like speed sessions, and
Yeah, it's like you better
Rather
finish
than-
the lecture set
like
beforehand.
I
Yeah,
think
you'd be
it's
so
defeating the
lost.
purpose because we're not actually discussing anything. We're just like, this is what I got. Blah, 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 blah.
Yeah. I mean, to be fair, these questions don't really have anything to discuss. They're very like, you know,
Yeah,
what is this? What is that?
yeah.
But I do think that it comes with like after absorbing everything.
Mhm.
Like you can't just like get it right away, I feel. I mean, some are easier than others, but some of the stuff it's like it takes like a day to absorb, and that's like kind of how we did it before, where we did the questions after the fact. So I don't know.
Well, all right. I'll see you guys in the main room.
Okay, bye.
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 Bye, guys.
Okay, we should all be back. I can see the second room is probably lingered, or one of the two rooms lingered. Now it looks like most people are back. So the first question, there's no, is about specific examples of the general functions of blood. There's no real essay on that, but of course it's built into the whole discussion of essay 6, because it asks about what are special things that help blood do its job. So is there a spokesperson for these first 3 questions about blood?
Hi, Professor. It's Jasmine.
Oh, okay, Jasmine, great, thanks.
So I'm doing number 1. It says give 2 specific examples of each of the 3 general functions of the blood. So the 3 functions are distributive, regulatory, and protective. So distributive, we put down blood delivers oxygen and removes carbon dioxide. And then the other one is it brings nutrients and hormones.
Perfect.
And for regulatory, we put down temperature, where the blood is a heat reservoir at 38 degrees Celsius. So if you need to warm some parts of the body, you can redistribute the blood in the body, considering that the blood is warmer than your core body temperature. So because the watery portion of the blood can hold heat, you can redistribute and regulate temperature within your body to maintain functions. Another one, we actually have a few. So we have volume, but I want to go over pH since I feel like you kind of went over that one the most. For that one, we put that the blood is a buffering system since it's slightly alkalinic, around 7.35 to 7.45. So the small changes in blood pH will be addressed rapidly because it's critical that when most of the body's cells work at a neutral pH. So because albumin is 60% of the protein in its plasma, it's the main buffer in protein in the plasma. Red blood cells are 90% in volume in hemoglobin, which also absorb the hydrogen ions and act as a buffer. So because the hydrogen ions generate bicarbonate, it is a product of some of the buffering as well. And for the third function, protective, we have immune and clotting, and we all agree that those kind of go hand in hand. So blood clotting is a way of preventing excess fluid by bleeding, but also it prevents entry into the blood from further microorganisms. That's what we have.
That's great. I had nothing to add to that. That's really well done. Okay. What about the plasma? Are you still speaking, Jasmine, or someone else? It asks about listing 6 plasma proteins and giving a function, and you gave one, which is albumin, and one of its functions as a pH buffer. What other things do you find in plasma that are proteins?
Professor, I can do that one.
Okay, thanks, Manri.
So my whole entire group didn't go through all of them, but we did go through the first few. So the albumin is obviously for buffering, and it also has a major role in osmotic pressure and also transport. And for alpha and beta globulins, they're antibodies and help transport lipids and toxic minerals. And they make up about 36% of the plasma proteins. And then for gamma globulins, we just put that they're antibodies. But for fibrinogens and prothrombin, if I'm saying that right, we didn't get to the general functions of those ones. We weren't really sure.
Okay, great. We'll go albumin, and we're going to go back to where our discussion of perfusion and osmotic pressure, because it makes up 60% of the protein in plasma. It is the major influence on blood protein, but the remaining part, the alpha and beta globulins and the gamma globulins, also are the most of the rest of the protein. I mean, we're talking over 95% of the protein. And it's that's contributing that osmotic pressure. So we'll come back and look at that in a minute. The globulins are a group, and 2 of them, alpha and beta, we're just going to be lumping together and not distinguishing which one's alpha and which one's beta. And under those, there are different members, some of which are the ones you've mentioned, and I don't remember whether it's an alpha or a beta, but prothrombin is one of those, and it's going to be really important in our discussion of blood clotting. There's another one we talked about, angiotensinogen. Do you remember that from making angiotensin 1 and then angiotensin 2? There are plasminogen we're going to be talking about, important in the breaking up of blood clots. These are all under this umbrella of alpha and beta globulins, as well as many of what be important in blood clotting called clotting factors, which we'll just leave at that name. We're going to not be more specific than that. Now, everybody that I've mentioned except the antibodies that Manreet brought up, the gamma globulins, are all made by the liver. So one of our other themes for this whole semester is how important the liver is to the functioning of our body in many, many body systems. So if we look at what affects osmotic pressure, well, liver function does. So I know we may not get to the red blood cell group, so we'll come back to that. But let me just, because we're doing, we want to finish up doing the essay 5, let me share the screen and talk about the role of, let me get to that, if it will. Yeah, there we go. Changing the blood osmolarity. So one common thing that can go wrong in patients is that they may have liver failure. The liver is a huge organ. It's also pretty regenerative. It tends to try and heal itself, but it may not be able to, if you're going into liver failure, to make enough albumin, enough alpha and beta globulins, and that could have, effects on pH and other things, blood clotting and such. But one of the other things it might affect is it might change this number, right? So if we do this, let's go back to the original numbers. If we say our hydrostatic pressure is 35 on the arterial side, and on the venous side, it's 17 for the hydrostatic pressure. But then we make the osmotic pressure, maybe I'll change it again. The osmotic pressure over here, instead of being 25, this person is in liver failure, then we make this osmotic pressure maybe 20, make it pretty dramatic, 20, and over here it's still 20. So what you're seeing is that coming out this end is now 15 instead of 10 net filtration pressure. And what's going in this end is only 3. Are we all right? That means instead of leaving 2 out here, we're leaving 12 in the interstitial fluid. And what is happening to this person is that you're seeing swelling of your, well, it depends on where it's happening. Sometimes in liver failure, it happens and their legs get swollen. And that's because their interstitial fluid is being left behind. That means also less is going back into their venous blood, but as long as they stay hydrated and drink enough, they may be able to make up for that and keep their blood pressure up. But they keep losing this fluid into their tissues. When you have excess fluid in the tissue, it has a term.
Edema.
Edema. So this would lead to edema or excess fluid in the tissue. Sometimes it happens just in their abdomen and they get these very swollen, fluid-filled abdomens. In fact, a kind of funny story, it's not funny in a way. We dealt with the blood pressure being low, but sometimes blood pressure is chronically high too, right? So if we change that number over here, instead of being low, instead of 35, and you should play with these numbers, let's make this 40, and that's maybe an extreme. So now you get 15 out here, and this drops to 20, you're only getting, 5 to go back in, that's going to lead to edema as well. Because what's staying out here is now not 2, but 10 remains out here, right? In interstitial fluid. I hope I'm not doing the math too fast. Well, my grandfather had this going on, and the fluid was collecting in his abdomen. And he was an immigrant, had like elementary school education. He was a very smart man, but he had only elementary school education in Italy, where he was from. So when he went to the hospital with this issue, and they basically tapped the fluid from his abdomen, needed to understand what was going on. So he was amazed at the weight loss he had by being in the hospital. But it was just fluid that had been accumulating due to his chronically high blood pressure. So we are going to wind it up here. Group B is going to start our discussion next time with talking about red blood cells. And we're going to start that by first talking about their histology. And they're pretty amazing. They're one of my other, I'm really impressed with, hemoglobin and red blood cells. They are amazingly efficient at doing their job. So this is the beginning of Essay 6. We should be able to, by Tuesday, easily finish Essay 6. Now, 6 is very straightforward. You really can go. It's big because it covers a lot of territory, but it's kind of like the cardiac cycle one, that if you read, page X to page X plus 5 or something, you could find all the answers for Essay 6. It's pretty darn straightforward. So we'll go through that. And that brings us to the last essay. We have about 12 days or something before the exam, which is blood clotting. And that is fairly complex, but I simplified it massively for you as far as the detail that you need to remember. So use the slides as a guide to what you need to know in hemostasis, in blood clotting, because I've really edited out a lot of the Roman numerals that you don't need to know for the clotting factors. So go ahead and read it in the book, but realize you don't have to know all of these. Let me just check the chat before I leave. So people are forgetting what group. So group B was working on the question about the histology of red blood cells. It's lecture question 3, 4, and 5. If you want to work further on that, then you are in breakout room 2, and we'll talk about that when we return next time. Okay, so remember to bring to lab the blood pressure handout. We're going to be looking at Kevin's video. There's a bunch of things in the PowerPoint study guide that we're going to go through. There's some theory about hypertension we're going to be talking about, because we've spent a lot of time with hypotension, low blood volume. We're also going to be talking a bit more about hypertension and the causes of it. So I'll see you in about, whatever it is, 15 minutes, and in lab. And then again, if you are coming to the second lab, I'll see you at about 1 o'clock. Okay, so take a break, and I'll see you soon.